Hi, my name is Philip, and I'll be presenting our work on non-attributable cyber threat intelligence exchange. The exchange of cyber threat intelligence primarily involves the two parties shown here. On one side, you have the intelligence community that has information about the motivations, capabilities, and the intent of the adversaries, but they often lack information about how these adversaries conduct operations. The how is largely held as artifacts in private entity networks. These artifacts are left behind by the adversary. Both sides have a desire and often a mutual objective to tie the observed behavior with the profile information of the adversary. However, timely and effective correlation rarely occurs. Clearly, the threat intelligence community cannot easily share information because of information classification and clearance requirements. And private entities also have barriers due to the sensitive information which may reside in some of those artifacts and the cyber observables, and also the possibility of public attribution of even having the adversarial activity occur in their network. Our work derives from several recent advancements in a few technologies. First, permission blockchains are becoming more prevalent and feasible to broadly use in applications such as web-based applications. Also, the need for anonymity in cryptocurrency transactions has spurred innovation in zero-knowledge proofs. And there's also been some recent work in cyber threat intelligence exchange over blockchain technology. Our work proposes an incentive-based chain code for exchanging cyber threat intelligence, but it uses some of the recent work in zero-knowledge proof ZK snarks that removes the barriers associated with named attribution in cyber threat intelligence sharing. We look to, we look to the blockchain to provide trusted, non-attributable authentication services. The most well-known example of blockchain includes cryptocurrencies such as Bitcoin and other altcoins, and then smart contracts, which is more commonly known. Ethereum is more commonly known for. Blockchain for applications is an emerging model where the blockchain network provides an underlying protocol from which to build distributed applications. The network consists of a consortium of trusted peers serving to validate transactions, and the blockchain ledger provides decentralized transactional validation, but applications can be developed to serve data through a relational or NoSQL database. So while adding or modifying the data might incur additional overhead in maintaining the blockchain, querying the data functions the same way as any other web application. The permission blockchain closely models the cyber threat intelligence community, where a consortium of national agencies, CERT teams, and industry trade groups share the curation of threat intelligence. Various private sector and other entities both consume threat intelligence and share the event artifacts. The data model centers on standard cyber threat event reports based on the Malware Information Sharing Platform, or MISP, where cyber threats associate with observed activities. Then work records provide a ledger for cyber threat intelligence exchange based on tokens in the proposed network. The primary users of the network are security operations centers. These are outside of the distributed system blockchain network. And this is where security analysts and threat hunters continuously correlate observed behavior in their networks to known threats or to suspected threats. Our approach to CTI exchange models analyst-to-analyst communication, in which the primary threat sharing barrier is the entity attribution. So imagine an analyst observing some unusual activity or event in their network and wanting to share more about it. Even querying the threat sharing community comes at a tremendous risk of law enforcement or other agencies taking that query and associating with some threat activity and then taking that event out of context. So to overcome this barrier and enable online threat sharing, we need a mechanism to authenticate anonymously while maintaining the transactional integrity. To achieve non-attributable use of the network, we look to token exchange for both incentivized transaction integrity and private authentication. In our zero knowledge system, tokens are maintained in a Merkle tree, and the Merkle root is maintained on the ledger for token transactions. Token ownership is not private in our scheme. The privacy comes in the proof of ownership. For authentication and token spending, the user must construct a ZK snark proof of having a valid token without having to identify which token. And now introducing the non-attributable use increases the possibility of free riding or flooding the network with a lot of low quality data. The permission blockchain exists to incentivize work and serve as a gatekeeper to control the value of cyber threat intelligence for the community. An entity requests the work of CTI curation by submitting a query with a valid token spend. The chain code queues the work, then users who are identified, there's no reason to, if you're working on threat intelligence, there's no reason to do that anonymously. And you can perform this work by answering queries such as which threat group is tied to this IP address or to this URI. And the work is incentivized by the token exchange, the same token that's used for authentication. And because of the incentive, additional states are necessary for decentralized and independent evaluation of the work performance. Finally, the work gets added by updating MISP records with improved information. And foreseeably, the entire network, not just the querying entity, receives value by this new intelligence. Other entities, security operations centers, that they can query these same MISP records to gain better insight into potential threats observed in their systems in their network. The mechanism of awarding tokens is straightforward. The network collectively maintains a Merkle tree, and new tokens are added to the leaves of the tree. The Merkle root itself seals the token inclusion on the blockchain, but a valid root can be calculated at any time. And timing is important. Otherwise, the root used for proof of knowledge might reveal the awarded token and therefore the identity. For example, if I receive a token at noon on a Monday and then later prove that I own the token by using a Merkle root that also was generated at noon on Monday, an adversary only needs to simply look up the token award occurring at a similar time as the Merkle root to identify the user associated with the transaction. So to counter this attack, the Merkle root is calculated and tree updates are broadcast to the network at some regular interval. Then each user and entity updates their tree structure because this will be necessary for constructing valid proofs. So any leaves on the tree that are necessary for forming the Merkle root are updated at that regular interval as well. So for example, if I were awarded a token, then I may have to wait for the next tree update, possibly within the hour, to use the same token. But when I spin, everybody's using the same up-to-date tree for proof construction, so there's no attribution to even recently awarded token. And these tree updates don't have to be performed continually, but really only when the user is wanting to spin. The tree distribution now would also be problematic if we were using a system similar to Zero Cash, which is configured to store coins in a 32-level Merkle tree. Such a tree would require 256 gigabytes, and hourly distributions would be all but unfeasible. Instead, our scheme uses branching to minimize the storage and distribution requirements. The network only needs to keep and distribute a very small portion of the tree to support the maximum number of entities. Then each entity stores a sparse Merkle tree based on the number of users that they maintain on the network. Then further, users can store a sparse Merkle tree to maintain their own wallet, to even have it further hide in the number of tokens that users can maintain. So because the network broadcast requires a full tree, we keep the tree height very short, and then the sparse Merkle trees maintained by the organizations and the users only require logarithmic storage relative to the full tree. Spinning a token requires a valid proof. Tokens are similar to coins in zero cash, but we simplify the construction scheme because there's no need to support currency in off-network transactions. Instead, the token is constructed by a secure hash function of the user's secret key and an arbitrary serial number. Then the proof uses a valid Merkle root and reveals the serial number as public data for proof validation. The user's secret key and Merkle path nodes necessary to calculate the root are kept secret. A valid proof is one in which anyone on the network can construct. If the proof is valid, then the chain code must also verify that the root is used, that the root used for construction is also valid on the network. And then finally, to prevent double spending, a list of spent serial numbers is necessary to be maintained on the network. If a user attempted to spend their token again, then the serial number they produce is publicly known by the distributed blockchain network to have already been spent. The ability to provide frequent tree updates allows for convenient authentication services such as revocation. Revocation can be difficult to achieve with anonymous authentication, but with frequent tree updates, the entity or network need only set a node of a user or even an entity to null, and any tokens previously issued to the user are no longer valid from that time forward. For implementation and testing, the height of the network portion of the tree we set at 14. And this only requires 1 megabyte of storage and network distribution to the network peers. And then the additional sparse tree storage required by entities and users is logarithmic. So the limiting factor for tree height is the proof construction time. In our testing over a single CPU, a tree depth of 128 level tree required 4.2 seconds to then construct the proof, which for an analyst to analyst work request transaction, we feel that would be acceptable. So in conclusion, we've provided a new approach for overcoming the trust barriers of interorganizational threat sharing between private and public entities using a distributed ledger technology. We've also demonstrated a novel use of ZK snarks and sparse Merkle trees to enable anonymous authentications and anonymous token spending for permission users. And we believe this will pave the way for new approaches to sharing cyber threat and intelligence, which not only reduces the barriers, but also commoditizes this difficult work of curating cyber threat intelligence. And overall, the participants in the network receive a greater value. Thank you, and I look forward to your questions.